Thank you for the introduction. And kudos for continuing the Warsaw Ruby Meetups, because we couldn't do it with Piotr, post-COVID. So, you guys really, you made them better than they ever were. So, yeah. We never offered free beers, so, Anyway, yeah, hi, I'm Tomasz. I'm going to give you a short talk about more or less the lessons and attitudes and approaches, and sometimes surprising, surprising depending on like where you are on your journey, but sometimes surprising learnings, some of them counterintuitive actually, and some of them kind of like open questions from scaling a service that runs at pretty decent scale, makes very decent money. I don't think I can share the exact numbers, but let's say there are, I think, 60 people at the company, and the service pays for their salaries and more, despite pretty high costs of acquiring a single customer. And it all runs as a Rails monolith, which is not surprising to anyone, right? We have like great Rails monoliths operating in the wild, like GitHub, like Shopify, and all the stuff from 37 Signals. But this one is actually running on Heroku, which is a name you probably haven't heard in a while. And whenever anybody talked about like big business, big money, and also big scalability. So, and also when somebody's talking about AI or AI startups, like Heroku is definitely under the radar of anyone here. So yeah, I'm Tomasz. You can find me almost like anywhere by going to tomasz.eu, or like this also like the Blue Sky handle, and so on and so on. So the subtitle is like, how far can you go with a Rails monolith on Heroku with a single database? This was basically always considered like a beginner stack. There was a time when Heroku offered a free plan, and you could deploy your first Rails application totally for free, get like some basic Postgres, I think even some basic Redis, and a single fraction of an instance to run your application. So Heroku was very friendly to beginners, and because of that, and it offered zero operations approach to deploying applications. Not only Rails right now, but you can deploy like a lot of different languages, and basically anything that can be put in a container can be now run on Heroku. But because Heroku always did it with this zero operations approach, zero operations promise, it was also kind of like considered to be a sort of like a toy or beginner stack. And it's been like this since Heroku started, something like 15, 16 years ago, even though nobody has ever come close to how zero ops Heroku actually is. So it's still like a golden standard. And even if you see like recent announcements from Rails, for example, working on Camel 2, they still use Heroku as the comparison point. Like like in the official docs or in the talks given by DHH, there's clearly stated, and DHH even said that in the recent interview with in Lex Friedman's podcast. We want to make hosting and deployment as easy as it is on Heroku. Heroku has been around for over a decade and a half, and it's still an unmatched easiness in hosting. But in terms of beginner applications, what about scaling up, right? Like, well, what about stuff going up seriously? But also, this talk is not going to be about Heroku at all. Anyway, and why is it not showing up properly? Hold on a second. What's up with the image? Oh, wow, something broke with my... okay, maybe it's even better. It's a bit of censorship, kind of. So what we're dealing with here, the product is called Candy AI, and it's a Rails application through which you can talk with an AI boyfriend, girlfriend, basically interact with a lot of AI models behind the scenes. So there are language models, there are image generation models, there are voice models. You can basically call your, virtual boyfriend, girlfriend. And yeah, I see some people laughing. That was exactly my reaction when I heard about it, when I started talking with them. It sounds like a very niche product, and I was surprised at like how many users does it have, how many paying users, because you cannot do much on a free account there, and like how much of growth it has, how popular it is. Yeah, I mean, here we are in this new reality. It might seem weird or funny, but it works, and people find use for it, and people pay for it, and it's like, you know, and if you try to use it, kind of grows on you, like, you know, like what, how can you use it? Like, you know, like sure, like some people use it to like play out their like pretty weird fantasies. But maybe it's better if they do it with a robot instead of a human being, right? Some people seem to be using it for kind of like training or trying out like some, you know, some lines or some approaches. I mean, I don't know. Like this is a question to our, like, you know, data science guys. I'm not looking at production data other than what I'm going to show with like, you know, with Postgres. But yeah. Anyway, this stuff has a lot of traffic. Okay, what the hell is with this presentation? You know what? Let me give a second. I think because I have it run in PDF mode, so that I can print it. But I can export it to PDF. But I did it already. So I don't need you anymore, PDF mode. Yes, now it's here. So some traffic. Database is a total of 1.2 terabytes. Not very impressive. I think you can even right now get a Mac computer with this sort of storage, if you pay a lot of money, but I think you can. But the other numbers are making this stuff hard to operate. There's 1 million messages written daily. So basically half of it written by humans and the other half as responses created by LLMs. There's 1.5 billion, that's 1,000 million for people who are always like, you know, confused by the weird Polish and English and French cardinals. So that's 1.5, you know, thousands of millions or millions of thousands or billions or 10 to 9 messages total in the database. And yeah, basically there's like 1 million of them created daily. So you can basically see like when this database is going to like double in size and so on and so on. They're not just messages, but messages are over half of the database and over half of the indexes. The indexes take 300 gigabytes, and only because I shipped a change yesterday that reduced it from 400 gigabytes. That's a lot, and why it's problematic I'm going to say in a while. And the growth of indexes, again, in a second, why it's problematic, is around 1.5 gigabytes of indexes a day. So why I'm not touching on the growth of the actual, well, okay, I am, but let's say I didn't. Why I'm not touching on the total database size, but I am touching on the index size. I'm going to get to that in a minute because this is, again, not going to be a Heroku talk. This is going to be a Postgres talk. What's the source of, well, my salary, like why I'm hired there, is that the service has 10 to 20% growth rate month over month, not year over year, which basically means that the traffic and the volume of data triples in a year. This is a lot. This is basically stuff that most startups and products see spread over like 3 years, and you usually have like a bit more time to react to some changes and to some challenges. Here it's sort of like I'm looking at some of our performance numbers, and I say to my CTO, listen, I think this thing might be problematic and we should probably optimize it. And he says, yeah, okay, you can work on it next week. And the next day, he comes to me and says, you have to work on it now because it just blew up in our face. Which is kind of fun if you kind of like get into it. Yeah, it's pretty surprising also because, and that's one of the lessons, nobody can predict not what's going to fail. This is being a terrible engineer if you cannot say what's going to fail, but nobody can predict the usage patterns of your application. So, you know, what's going to grow, if people are going to make more calls, if people are going to make more messages, people are going to generate more pictures, which means that you don't always know what's the next thing that will need optimization badly. So what have we learned so far by the growth rate? And remember, we're still talking about like, you know, tripling traffic in a year. That's the counterintuitive thing, and the thing that might not be very popular with other engineers, and something that myself 10 years ago would boo off of stage screaming, you know, bullshit, fuck off, and like, you know, you're not a real engineer. In the initial stage of product or a startup, especially if it grows, if it's supposed to grow, you build features. You ship, well, not build, you ship features. You ship features, you get the momentum, you get people attracted to your product, you get people hooked on your product, you get the usage patterns. There's a beautiful saying, and I really like that this talk is supposed to be given in English, because in Polish you don't have an analog saying. You throw stuff at wall and see what sticks, which means that basically you build 30 features and you're probably going to be removing half of them, 6 months from now, if it turns out to not be working or not be bringing in revenue or not be bringing you a competitive advantage. But it also means that in the initial stage, anytime you spend on performance optimization or thinking about performance is time wasted. Like seriously, like if you're building a startup right now, or if you're going to build a startup, you should forget about the stock. Maybe not exactly leave the room because it's going to make a bit of a noise and interfere with other people wanting to hear it, but don't care about performance, not because performance is like bad or wrong. It's that first, you don't know what's going to be the performance problem, because again, you don't know the usage patterns of your application, of your database. You don't know the trajectory, you don't know which features are going to be built on top of that. You can build a wonderfully designed database structure for a single feature, and then your other developer is going to go on a talk like happening in one of the other rooms here right now about vibe coding, and he's going to vibe code the shittiest database structure producing like m multiplied by n complexity queries, and your super optimizations are still going to be wasted. So you don't know the trajectory of both your customers and your further development. You don't know how and where stuff will grow. So again, but also the biggest problem here is that working on performance should be number based. Like, there's vibe coding and there's engineering that's science based. Science based means being numbers based, or being at least numbers informed, numbers driven, which kind of like unrolling this means that any work on performance should be based by numbers. You cannot go like, if you're a serious engineer, you cannot say, I think this will cause performance issues. You should be able to show and say this is causing performance issues on this and this amount of data. Sure, you don't need to wait for production to fail at a certain stage, at a certain size, because you know that there should have been an index. But at least you should be able to show that by not putting an index, when this database grows beyond 20,000 records, the queries will begin to be noticeably slow. If you cannot demonstrate it, I'm sorry, but you're not suited for working on performance. And again, if you want to be suited on working on performance, you need to know how to make those measurements, how to make those experiments. But also, because on small data sets, if you have like a small table that that's not going to have more than a dozen of records, or 20 or even 100. For example, for us, it's a table that we call servers, where we basically define endpoints to our in-house AI endpoints. We have 4 text servers, 4 image generation servers, a couple of moderation ones, and so there's maybe 20. If there was never a single index on this table, not even on the primary key, nobody would even notice. Nobody could tell that there's no index on this table. But at the same time, you have the messages table with like over 1 billion records. Let me tell you, if you try to find anything in this table in different way than getting it through an index, oh, good fucking luck. So it also means, and also just to give you like a perspective, 1 gigahertz, and even your phone now has like 1 gigahertz clock, means 10 to 9 operations per second, which means that, and again, sorry for putting numbers here, but we are engineers and we're talking about being numbers based and being engineers. Even if you write terrible code that's going to take a collection of 1,000 records and is going to do n square operations on it. So it's going to take 1,000 records to a second power. It's going to make million operations, so like million cycles, million iterations in total, because there's going to be a nested loop. You're still talking about million operations on a machine that is basically suited to make 1,000 of that in a second. You probably will not notice. I mean, okay, if it's going to take a second, you will begin to notice, but this is the breaking point. Like if you make a very terrible algorithm and it's going to, and you're beginning to have like a decently sized data set. So so far, like, if you were to forget the rest of the talk, if it's too boring, you pick up your phone, you decide to like doom scroll anyway, you're going to step out of this room and say, yeah, Tomasz basically said that you shouldn't performance optimize. I can live with it, but let's go further. One more argument against working on performance, sorry for doing it, is economy. And economy is not only about money, it's about comparing money. And you might think that well, okay, if we do this optimization, let's say you're a well-paid engineer, very well-paid engineer. Let's say you make, I don't know, like $10,000 a month. It's going to take me 2 weeks to make the performance of this and that part better. So it's going to cost the company $5,000. No. What it's going to cost the company is you not working on delivering extra value, extra features to the product for those 2 weeks. And, if this feature that you would build in 2 weeks would bring the company, 10 or 20 or 30% growth in revenue, that begins to be money that's like way, way more, especially spread over, I don't know, like 12 months, than those 5,000. Of course, nobody knows the hard numbers. Nobody knows how much, again, because we throw stuff at the wall and see what sticks. Nobody knows how much this money will bring in. And maybe we are going to be at a breaking point where not doing the performance is actually going to drive users away. So yeah, this is the hard decision. This is what the big bucks are for. Deciding, okay, is it worth building the feature or is it worth optimizing what we have right now? My observation from being in the industry for 18, 19 years now is that teams and projects that have a lot of time for performance tuning fall into one of two categories, both actually pretty similar. They're either doing performance critical software. We are not. We are doing web applications. I mean, come on, like 200 milliseconds to do something. People doing automotive engineering would kill for having 200 milliseconds to do like the entire cycle of whatever they're doing. Or they work on products of no growth. And, excuse me? Timestamp is in milliseconds. Yeah, so this is a precision. But I don't understand the relation here. Yeah, but like anyway, milliseconds, right? Like we have milliseconds, or we aim to operate in milliseconds. How many times does a car engine have to inject fuel? How much time does it take to calculate the amount of fuel to inject, and for how long to open the injectors, right? Like this is and this is like a hard real-time system. Basically means that if the computer doesn't make this calculation in this time, the whole system should fail, because otherwise it's a safety hazard. Anyway, or the teams that have enough time for performance tuning, that can spend a lot of time on performance tuning, are products that don't grow. And there's nothing wrong with that, right? We have products where we don't want new features to be built. It's just that this talk is not about this. This talk is about terrible growth rates and how fantastic beasts and how to deal with them. The cost of working on operations. The cost of working on operations kind of factors into it. I mentioned imagine that I spent 2 weeks working on something. Imagine you have an engineer who takes his entire salary and spends only time on making this stuff run. He's usually called a DevOps or an admin or a site reliability engineer. It kind of like depends whether they code in Ruby or in Go or in some other technology. But in quite many organizations, there's this person called admin, and they spend their entire time making sure that stuff runs or that stuff can run, and it's one huge salary. And we could have an engineer for the same amount of money who would be actually like delivering features. Anyway, and this is where kind of like Heroku shines. Heroku forces a very specific application approach that makes it actually easier for Heroku to advertise itself as zero ops and kind of like make this stuff easier for for us, right? It's sort of like give some, take some. We have to make some decisions. We have to make some concessions to be able to deploy on Heroku, but then in return, we are getting a zero ops platform. So there's there's the 12-factor app. It has like an entire website now. It's now codified. What's a 12-factor app? Doesn't matter. The important stuff is there's no double server setup. Like there's no Nginx and Puma. There's just like everything is served by the Rails application server, basically Puma. The ephemeral or immutable file system. Now, those two words do not mean the same thing. Immutable file system is immutable means something that's solid, cannot be changed. Ephemeral means something exactly the opposite. Something that's like in the air, not solid, something that can go away. Why am I using one as a synonym of the other? That looks like if somebody tries to show you this, you should scream bullshit, right? So immutable file system in operations means that the application or you or like whatever does have a file system, and operations can be made on the file system, including invasive operations, because, well, you need to be able to write to a log file. You need to be able to have like some file descriptors that you can write to, or process an uploaded file before you put it somewhere else. What does it mean is that all the changes that happen on this file system actually don't happen on the actual, like, well, we don't even have a disk, right? Let's say we have a file system that's in RAM, and all the persistence happens, let's say, in also RAM. And whenever the application reboots, gets redeployed, it goes away, which basically means that there's a share nothing philosophy also. So the applications don't like share any files, so don't share any file systems. And any state changes that you want to persist, they need to be put outside of the application, outside of the application server. So if again, coming back, if you uploaded a file to your web application, I don't know, an image or anything, and you need to process, application needs to process it, sure, let the application process it, but then it needs to be put somewhere outside of the application's file system. In I don't know, in Cloudflare, in AWS, in Google buckets, anywhere, but it cannot be persisted in the application file system, because this file system is going away on the next reboot, probably. And this approach actually allows Heroku, and like, it's and with this approach, it's actually pretty easy to scale horizontally, because because if you have like this shared nothing approach, immutable file system and stuff, it basically means that you can deploy 50 applications, 50 instances with the same copy of the application, as long as you add each of the 50 to your load balancer, and you're good, and it just works. The ops community, the DevOps community, the admin community, I don't know what's the like current nom du jour for people doing administration heavy stuff. They have rediscovered the beauty and scalability of this approach of containers, right? Containers are very similar. Like by default in containers, your file system is going away when you restart the container. I mean, you can of course like do mount points and stuff, but you have to be very explicit about it. But also it means that if your application can run in a container, you can put again 50 of them, and you can serve 50 clients at the same time. Excuse me? Containers, virtual machines, instances, right? Like anything that can run your application, whether it's physical computer or any layer on top of it. Now, where does it bring us? Okay, so we've actually already established that, okay, let's say file storage and serving, it's a solved problem. We put it on AWS, we don't care, it works. It scales. Because, well, if it doesn't scale for Amazon, we have a different problem. Application scales horizontally. Again, not a problem. We put 50 of those instances, containers, whatever, it just works. Which also kind of underlines the fact that performance is not an important issue, because even if you wrote crappy algorithm, you can just put 5 more instances so that your users can still have like a decent service level. This is not the best engineering approach. It's actually a pretty bad engineering approach, but it might be the best business approach, because one more instance costs the company, let's say, $50 a month. Again, me spending 2 weeks or you spending 2 weeks on optimizing it costs 5,000, and 5,000 just the salary, not talking about the alternative cost of not building a feature that could bring like millions. So what's going to be our bottleneck? Database. If the database is your bottleneck when you're scaling up, you're doing your job well. This is what should be your bottleneck. Why? There was this famous, well, not famous, but like there was this very insightful tweet which put it nicely in a single sentence, and I cannot find the source. It's probably will got deleted off of Twitter. Your application is going to have a shared mutable state. If you ever did functional programming, you know that shared mutable state is bad. You should never have shared mutable state. The problem is that if you're doing web applications, you do have shared mutable state, because otherwise there's no point in putting it on the web for other people to interact, right? So your application is going to have a shared mutable state. And you want this shared mutable state to be Postgres. That's it. Oh, or MySQL, right? But like what I'm saying is that there are a lot of very smart people, way smarter than me, who have put like 20, 30 years of developing those database engines, and exactly for this one single purpose, to be a good, working, scalable, short, mutable state provider or service. So I want my problems to be centered on the database. Shared mutable state is the only difficult thing about scaling web applications, and I'm pretty sure that some of you might have like a couple of questions or objections to it. I'll be very happy to discuss it after the talk. So this is now Postgres talk. Forget about Heroku. Heroku just offers Postgres as your default or only database, right? But you know, this is now Postgres talk, because Heroku is not a scalability problem. Rails is not a scalability problem. PHP, Java, Python, this is never going to be a scalability problem, unless you use Node.js on the backend, in which case, like, you know, fuck off. But if you're doing web application right, your bottleneck is your database. And let's talk about scaling from a perspective of working with database, and specifically from the Postgres perspective. But most of those lessons are applicable to MySQL, especially since 2019, but I'm not going to spoil it. So there are 3 levels for a software developer. I'm not saying database administrator, database expert, you know, database consultant. There are 3 levels at which a software developer who builds features, or software backend developer who builds features in, you know, Ruby on Rails or even Python or even other technologies, at which this developer can become an expert or a master, or like have different levels of being able to work with, well, Postgres, but also MySQL since 2011. It's the explain analyze. There's no other skill that's required. Oh, I mean, okay, well, it's almost like saying, you know, there's not, the Switzerland is flat if you disregard the Alps, right? So all the work on analyzing Postgres performance, optimizing Postgres performance, finding bottlenecks in your SQL queries are about understanding and acting on explain analyze, but also about knowing when to not act on explain analyze. Sometimes explain analyze will tell you that your query is shit, and sometimes it's okay. So the basic skill is running explain analyze and just seeing if we have like a index scan or sequential scan. Index scan good, sequential scan bad. Congratulations, you can now add Postgres to your resume. Advanced is fully understanding explain analyze. This is well, this is not something I'm going to cover in a single talk. But basically, there are different levels of, you know, sequential scans, different layers, and sometimes even an index scan can be wrong. Sometimes you can see that sometimes explain analyze will show you that you know, it's great that you have an index, but I'm not using it, or I'm not using it well. This is also like an important thing to learn from it. Master skill is basically being able to make and not make important decisions based on the output of explain analyze. Not making is maybe even the more important part. We'll get to it in a second. And also, since 2019, this is not just Postgres. MySQL in 2019, finally, after like 20 years of hammering it, well, maybe 15, MySQL has finally added explain analyze to its arsenal. Because previously, I think you only had explain, which only told you how MySQL thinks it will execute the query. But the difference is with the explain analyze. I mean, there are like a couple of also different modifier keywords like verbose and stuff, but analyze actually runs the query and tells you what actually happened and in what times. It actually measures which stuff took some time, took what amount of time, which is again important because here I told you index scan good, sequential scan bad. But also if your sequential scan is over a table of 10 records, it's good, right? So you need to be able also to not make some decisions or not make some moves. Another lesson coming from databases and Rails and a lot of different stuff happening at scale. And also, I hope that this talk is not recorded because maybe my CTO will see it and there's a jab into my CTO. Oh, okay, sorry. Don't try to be smarter than framework and the database. Use defaults. The defaults in frameworks are usually really, really good. Like they're good and quite often battle tested by other people who had the same problems. You just need to remember that every index you add adds a cost on saving a new record, because beside the table, all the indexes need to be updated as well. But it's usually a fixed cost. Databases are optimized so hard that we can consider, I know it's mathematically not fully 100% right, but we can consider the cost of each extra index to be O of 1. So a fixed cost, a fixed time cost operation. So you're probably fine. Saving a record is always going to take some time in the database anyway. You probably like have callbacks and stuff and services and all lot of stuff happening. Adding 1 millisecond only because you've added an index and one more column, this is not bad. The bigger cost of index is actually storing indexes, but we're going to get to it later. Constraints, database constraints are a great tool. I'm not sure if MySQL finally has them because I frankly don't care and don't want to care about MySQL. The cost of constraint happens on delete. So whenever you delete a record, any constraints that reference this table from which the record is deleted, they need to be checked whether there are no broken constraints. And now if you combine those two things, if you have a constraint on a foreign key, you should have an index on this foreign key. If you try to be smarter than the framework and you add a constraint in active record migration, but added an index false, so you add a constraint with an index, you've just made my work super crappy in trying to investigate why suddenly adding a record to a table takes 20 milliseconds, but deleting it takes 2 seconds. And holy shit, I had this a couple of weeks ago. Turns out that somebody added code that created a constraint, but without that index, and it was fine, again, as long as the table was small, the referencing table. But the moment that the referencing table suddenly started having a million records, checking a constraint when I was, for example, deleting a character, and there was like a referencing table, referencing this character ID, suddenly checking against this constraint, if I'm not going to break data integrity, suddenly took a second and a half. Like, what the hell? Like, deletion should happen immediately, right? So don't try to be smarter than frameworks. If you are escaping defaults, make sure you really, really, really read what the defaults are, why you are escaping them, and what are going to be the costs of escaping them. And also, there was like absolutely no reason to add this constraint without an index. Like there was no requirement to do it. It was just somebody's creativity of like, yeah, this other table is going to be small, and it was small initially, so we don't need an index there. So this part of me saying that you don't need to think about performance, that wasn't true. Like if you're going to be stupid, then of course it's going to be costly later on. Another thing that you need when you're scaling up is a good enough observability. I'm not saying great observability. I'm not saying best observability. If you have a monolith, and this is the monolith part of the talk, you don't need distributed traces. And I love distributed traces. I love OpenTelemetry. I have a talk about OpenTelemetry, about like how great it is and like how good it is to use it, like in Honeycomb or in Grafana. But the thing is that if you have a monolith, you don't need distributed traces because, well, you don't have service distribution. You have a single monolith, right? But what you need are your SQL queries to be tracked somewhere. So you're probably pretty good with logs, but at some point you're going to need to add some observability in your SQL queries so that you can see which queries take time. And it's not just to see a single query. Again, we are engineers, we're numbers based. If you're doing performance, you're going to be a scientist. I'm sorry. Which means that you need to be able to actually have metrics built on those numbers, which means that you need to be able to say at any given moment or see on the dashboards, what's your P50, also called average. P50 makes you sound smarter. What's your P90, P95, P99, and also P100, which basically means what are your slowest ones. What's P90, what's P95? If you're a scientist, you're going to have to learn it anyway, so I'm not going to repeat it. But basically, you will need to have those metrics. So, important thing. And then the second sentence, I love contradicting myself. You will need to know which of those to ignore. Not to disregard, you still need those numbers sometimes. But P100 is basically going to show what are your slowest requests, queries, transactions, parts of the application, routes. This is a bad metric to act on because you are always going to have outliers. There will be errors. There will be network splits situations. You might happen to do something in this second where actually the database might have rebuilt a part of indexes, or the connection could be flaky because we are doing it in a networked system, and networks are pretty unreliable. But the outliers can sometimes actually give you a glimpse of what might happen soon to the rest of your users. Another lesson, you might know it, you might not know it, Postgres is caching data, which means that, sure, having an application level caching mechanism is great, but do not ever cache raw data from Postgres. It doesn't make sense. Like, you're going to spend, you're going to like pay for the second time the amount of money and also with the amount of complexity of serializing and deserializing this data from cache, even though Postgres is doing the caching. And Postgres has pretty smart algorithms on what to keep in the cache, what to keep in RAM, and what to keep and what to leave on disk. So do not cache data. Cache the rendered views that are based on the data, preferably the data that's infrequently changed. Infrequently here means, as a rule of thumb, that's going to be read 10 times more often than changed or written, right? So so that you can actually get your value out of extra code and extra operations and putting it in extra storage like Memcached or Redis. So Postgres does the caching, which means that Postgres is using RAM memory, and you want your stuff to be in RAM memory, as everybody who ever deployed like Redis or Memcached can tell you. Postgres is using RAM for two things. I mean, of course, again, if there's like a very good DBA, very good Postgres person, they're going to like throw eggs at me. But basically, you can treat Postgres RAM as something spent on two things: indexes, first and foremost, and like the top priority, and whatever's left after putting indexes in RAM, the rest is going to be used for data cache so that it can be quickly accessed. And that sort of makes this thing of observing your size of indexes, which I mentioned a couple of slides ago. Let's see if I can browse to them without breaking anything. I was showing a metric that I'm on purpose observing, the total index size and the growth of indexes per day. And this is exactly why. Because I know that my instance that runs my Postgres has a specific amount of RAM, let's say 512, right? Half a terabyte of RAM, nice number. You cannot get a Mac computer with this amount. Which means that if I have 300 gigabytes, I know that I have at most 200 gigabytes left on my data cache. Which means that hopefully the users that are actively using my website are the users that use a fraction of the data, that read a fraction of the data, which fortunately for this kind of service is true, because let me show you back the service to remind you what it is. It's mostly about chatting with an AI model, which basically means that all of the users at most use maybe 5 to 10% of the messages that are in the database, because all older ones are somewhere in the scroll history that you need to paginate and scroll into. So fortunately, we're good here, right? But again, you need to know the usage patterns of your application, of your data, to make a decisions of like, okay, I need at least 100 gigabytes for the data cache for Postgres, which means that, I have 512, so that leaves me 200, nice, cozy, comfortable. But when this number begins to look like 400, 450, I know that I need to migrate my data to start caching, to start sharding or partitioning, or move to a bigger machine, again, VM or instance or computer, however we call it, because I might be running out of place for Postgres to store data cache. And what happens, and okay, yeah, so Heroku is great, but also Heroku sucks because Heroku is on AWS. Heroku doesn't run their own servers, and AWS does not put hard disks, so where the data is persisted by Postgres, with the machines using a SATA or an M.2 NVMe or any other standard that was actually designed for communicating between computer and the disk. It's actually using networked drives, which means that any disk access goes over the network, and you get like the combination of like the two slowest possible things, because there are also like hard disk, like spinning magnetic hard disks, which means that all the data that you don't have in cache, in Postgres cache, is going to be super slow to access. And the combination of having users who are like outliers, for example, somebody logs into the service after a month of not using it, which means that their conversations, their messages, all the data have long been purged away from the cache. And we have observability where we look at P100, so we look at outliers, look at our slowest queries. And Postgres has already booted their data out of the cache. Postgres needs to dig this data out of slow storage. Do we care about it? No. This is an outlier. This is in our P100. This is not in our P95. This is not in our P99. We should see it, that something like this might happen. Maybe we want to really optimize so that everybody has super fast access if we can afford it. But again, sometimes we need observability and we need knowledge about how stuff works only to say, this is fine with the fire spreading around. This is fine. We are not going to act on it. Next thing, indexes. Oh, shit. Yeah. So I hate this part. Indexes are always taught in every documentation, every course, as the solution to most of your performance problems with database access. And for 95% of the time, this is true. The problem is that at a certain scale, because again, this is a scaling talk, right? I don't know if you like maybe slept through the initial slide. At certain scale, you are going to run into situations where Postgres either doesn't use the index, even though it should, because it decides to work differently. It's considered a bug in the query planner, but like good luck reporting this bug, reproducing this bug, and getting someone from Postgres to fix it, and then upgrading your database half a year from now when somebody fixes it, and running your application for half a year with this bug present. So sometimes query planner shits itself. Sometimes query planner is operating because like query planner is not a wizard. And it's not magical. Query planner is like this underinformed human who looks at the table and, you could put me in front of the table saying, this is a table that has, like this many million records. But also, statistically speaking, there should be 90% of the records here should have this value. Or like the distribution of like this column's value, like for example, status, deleted or not, is like 90 to 10, which means that I should not use an index because what I would do is I would scan the index, take 90% of the IDs from there, and then fetch those 90% of IDs anyway from the table. Doesn't make sense. So it's probably better for me to do a sequential scan, right? I'm going to look into this large table. If it's 90%, the performance is actually better if I do a sequential scan, get all of them, and not use the index. The problem is that, do you see at which part I made? I was fed bullshit information. I was fed information that the metadata of the table says that 90% is this and 10% of this is that. Is different. It doesn't have to be true. Postgres keeps table metadata, but the table metadata cannot be refreshed all the time because we would get abysmal, terrible performance. So the table metadata is refreshed from time to time when you perform a vacuum or perform a vacuum analyze, to be specific. The analogy to explain analyze actually makes sense because it's about like what query, what algorithm to apply, what data source to use. If you delete a lot from your table, if you have like very volatile data, you will get your table metadata out of sync with the actual data, which means that it will throw query planner completely off the rails. Well, it will completely confuse the query planner. And if you confuse the query planner with bad metadata, guess what the Postgres maintainers will tell you? And they will be right. This is not a bug report. Fix your fucking table. So you need to run vacuum or you need to run vacuum analyze on a regular basis, but you cannot do it too often because what vacuum does, well, it goes through the entire database, it removes the dead tuples. What is a tuple and what is MVCC? I don't want to get into it because we are going deep into database lore here. But query planner also has its quirks. There is, for example, a very classical problem that in large table, if you do an order clause by, let's say, indexed column, you're fine. Or you do aware over another index column, and then you do an order over another index column. So, for example, you pick, let's say, all the messages that belong to a user or to a conversation. Conversation ID is indexed. The ID of the actual messages are indexed. Sure, we are not using the composite index, but we still should be fine because there are maybe, let's say, 20 messages in the conversation. Let's say there are 20. There's a very classical problem in large tables that you will never encounter until you get past a certain size. So this is sort of like a teaser or sort of like a jump scare, sort of like a horror story, that if I decide to get those messages of conversation, like remember, there's 20 of them. Messages table has like 1 billion rows, but there's 20 of them belonging to this conversation ID. If I pick all those messages without any order, I'm fine. Postgres will use the index. I get those 20 back. It will take 2 milliseconds. We're good. If I put an order by message ID, because I actually want to sort them chronologically and I have sequential IDs, so I don't want to have an extra index on created at, I'm just going to use ID as a proxy for the chronological order. Perfectly fine. and I do order and give me all 20 of them, order ascending, 2 milliseconds, I get all 20 of them back. Order descending by ID, 2 milliseconds, I get all of them back. Order descending limit 1, so I want to get the one last message from this conversation. I'm fine, everything's good. Order, but I want to get the oldest message. Order ID ascending limit 1, the query takes 3 minutes. And okay, so you might be going back to this, couple of slides and saying, well, okay, it was probably an outlier. Maybe it was a data that was like booted out of the cache. How you identify the outliers and data that was only moved out of the cache and taken from disk? That when you run this query for a second time, also one of the harder things because of this, it's going to complete immediately, and the explain analysis is going to show actually different numbers. But this one, I run this query for second time, 3 minutes. I run it 4, 5, 5th time. I know this data is in cache. I can bet my life on it that this data is in Postgres cache. It's in RAM. It takes 10 minutes. Why? Well, Query Planner is weird, and it can sometimes do very inefficient stuff. Like, for example, it can, if you look at explain analyze, because this is, again, the only weapon that you need to have in your arsenal. If you look at explain analyze, you'll suddenly see that it went over 60 million records only to discard 59, 999, 980 of them, ordering them for, let's say an efficient algorithm, but still 60 million records, just to give me one. And again, I'm encountering a situation where with the same order clause, but without the limit, it's actually better for me to get it all into application site and sort it in Ruby. Stupid? If anybody is going to see it on the code review, they're going to say, hey, this is not the way to do it. We should sort in database. Well, yeah, but then you can actually simulate, like you can actually reproduce this scenario. It's so deterministic, it almost hurts. And then there's yet another thing that I've learned pretty recently about, because also I was never a database expert. You can probably tell from this talk, right? There's another thing that indexes are built in such a way, especially indexes that can have null values, that they can either have nulls first or nulls last. And suddenly, if you have this query that took this variant of the query that took 3 minutes, so order by ID, ascending limit 1, so I want to take the last one. But I add the special clause, nulls first or nulls last, I don't remember which one, the query is again in 2 milliseconds. Well, why? Because it instructs the query planner how to treat the index to start from the beginning or from the end. And it suddenly decides, hey, this data is actually in the index. I don't need to go through 60 million rows, sorting them, and then filtering them by index. So Query Planner is weird. And at some point, you are going to get a PhD in Query Planner at a certain scale, if you want it or not. I'm in the process. I think I failed a couple of exams at this point already. But this is the sort of stuff you're getting into. The good news is that it's actually fun. It's actually fun to learn it, because you then appreciate a lot of thought and hard work that goes into Postgres and or MySQL, and like how much of complexity, of data management complexity, of computational complexity is kept in the database. But still, at the same time, you have enough reasons to curse. So it's pretty cool. You get humble, but you also still have grounds to complain. So then, also coming back to the RAM and cache question, when do you need to shard the database and go multi-database? When your index size is bigger than available RAM. Now on Heroku, the biggest available database instance is 1 terabyte of RAM. We have 300 gigabytes of indexes, which means what? Well, we can still grow triple before it begins to be a problem. And guess what was my CTO's answer when I said, hey, I think we should start sharding? His answer was like, well, this is your salary, and this is how much it will cost us to upgrade to a bigger database. And those numbers, they are not in the same ballpark, right? So we are going to upgrade. We're going to upgrade, and we're going to upgrade as much as far as we can go with, because sharding or partitioning is actually introducing a lot of complexity that you don't want to deal with until you really have to. By the way, actually with Heroku, it's pretty funny, because the largest available database instance only gives you like 30% more RAM over the previous one, but it costs over a double. So actually, you should escape you should not upgrade to the final possible database instance. By the way, I have no idea why is that. Maybe because it takes the entire machine. or something. Maybe they have some weird contract with Amazon. I don't know. On Amazon, you can actually get a bit bigger RAM instances. And also, by the way, when you're having a database server, RAM is the only metric that you look at. Like, frankly, like you can look at the amount of cores, the amount of storage. You don't care about storage because this is the network storage. You can always network more, right? You can always add more disks. RAM is the only thing we care about. Other metrics are not really viable here. I mean, of course, like, if you put a Raspberry Pi and you solder like a terabyte of RAM to it, sure, it's going to have terrible performance, but like nobody does it, right? There's a reason you cannot buy a motherboard that will support 1 terabyte of RAM that's going to support shitty CPUs. It still needs to be workable, right? But then again, when do you need to shard? Probably at this point, we haven't had to yet. So again, we are at this middle scale where we are not yet, this is far from big data. Big data is, and don't let anyone tell you otherwise. Big data is a specific category of science and algorithms and methods and tools aimed at working with data sets, not databases, data sets, so amounts of data, volumes of data that are bigger than RAM available on a single machine. Currently, a physical private person with no business, I can go to eBay and I can buy a server with 4 terabytes of RAM. So is 3 terabytes of data big data? Hell no, it's at most mid data. So this is why I call our service mid data or middle data or average data. Well, average is maybe no, it's not average, but it's not big. So you also need to know what is big and also when to start to scale and escape. So the remote stopped working. Maybe I went too far. Okay, so that's all. Thank you. I'm betting you have like a lot of questions and comments. I just need like 30 more seconds of your time and then I'll start getting questions, okay? Yeah, so there's one more thing. You might have known, you might have met, you might have been influenced by Piotr Szotkowski. He has sadly passed away. There was a funeral this Monday. So he was a great person in the Ruby community in Polish and European. You are probably, if you haven't even been like influenced by Piotr, you probably know a person who was influenced by Piotr, or maybe use open source where he committed. He was very prolific. So if you have, please go to this site. There's a Google form where you can write your memory about Piotr, what you remember about him, what's your like fondest memory, how has he impacted your life. This will be shared with the family, and if you consent, that's a separate chat box. It might be also published on like a website where we're going to build like this sort of like virtual memorial. Monument is a very pompous word, but like this sort of like virtual memory site, about Piotr. So I'm going to also publish it on a couple of social media. This is actually the first moment when other people see this link and see this form. So yeah, sorry for being a downer. He was my best friend and business partner, and like I'm still trying to get my shit together. So it would really help, the family, and if you remember Piotr, if you have like any positive memory of him, if you could add yours to this form that's linked from this site. Thanks in advance. So yeah, this is like a proper thanks. And if you have questions and comments, I prefer questions over comments, by the way, because I know that some of the claims here might have been controversial. Your experience might have been different, but again, I prefer questions. Yes, please.
First of all, really wonderful.
Do we have a second microphone? Or? No.
Yeah. First of all, a really wonderful presentation, very informative. So thank you for this one. And I have a simple, indeed, like 2 questions. First one is pretty simple. So, if you would start some new adventure with new startup, would you recommend as well Heroku infrastructure and similar, or like Kubernetes on Azure on other cloud, or something different approach?
And the second question?
Yeah, so later on.
Okay, I need to get my connection. That's a very good question, and that's a very simple question for me.
And sorry, about microservices and monolith architecture. From the scratch.
Okay, but like let's get to the second question then in a second, right? It's the best question that you should ask yourself when starting something new, right? Which stack do I deploy on? This decision to go for Heroku was my CTO's decision. I joined the company a bit later in the stage, and my CTO has a very simple answer, and it's an answer I fully agree with. Why did you do Heroku? Well, because I know Heroku. Kubernetes, I know there's a lot of YAML involved, but I don't know enough for Kubernetes. I know about Docker Compose. I can run some stuff with Docker Compose. But if I were to start a business, because like hobby application is a different story, right? When I do hobby applications, I want to get dirty. I want to get involved into operations. I want to learn this stuff. I want to learn Docker. I want to learn Kubernetes. I want to learn some different stuff. But if I was going to run a business that's supposed to be working from the day one and hopefully making money, and my time is going to be best spent building new features, because I expect the growth, I expect a lot of features and so on and so on, I'm picking Ruby on Rails because this is how I can iterate features, you know, the fastest way possible. I'm picking Postgres because it's the database with which I have the best experiences so far, even if the query planner, you know, can be weird. And I'm picking, and yeah, if it's a business, I'm picking Heroku because I can always get off of Heroku pretty easily, and yeah, I'm going to pay maybe $50 in my first month, and then I'm going to pay more if my business is going to make me more. But yes, I would. Maybe a year ago, that would be my first choice, but now I see that they do deliver on the promise of zero operations. So yes, I would pick Heroku. And the second question was?
About architecture, monolith. About architecture, like would you choose from the beginning, like microservices approach? Still, would you try to have from the beginning, or would you would just start from the monolith architecture, right?
I love when there are two questions and there's the same answer to both. Also, this place is being closed in 40 minutes, so I don't think we have time for microservices versus monolith discussion. And yeah, like let's leave it at that, right? But I've had experiences with microservices. I've had experiences with raised monoliths. Monoliths are easier for me to work with. They are, again, maybe more difficult in terms of, like, the size of the code base. But I think that by doing microservices, you are getting into operational complexity, because you are trading, you know, local inside the virtual machine function dispatch to a function dispatch over HTTP, which introduces you're trading code base complexity or single code base complexity for networking problems. So it probably depends. Probably there are scenarios in which proper microservice architecture, microservices are properly separated, where they are not synchronous. Maybe they communicate over, like, let's say, like a shared message queue or something. There are scenarios in which I can imagine microservices being the better choice. But for an application like this, also the one that uses, like, turbo frames and, like, uses a lot of the raceway stuff, monolith works. And if it works, just as Postgres and Heroku, like, you know, if it works, why change it? Are there any more questions? Or yes, please.
Thank you for your talk. So my question is about the process when you need to analyze big amount of data in one query. Which strategy do you choose to do that? In my head, I have like ideas like downloading the biggest possible to test it locally. The second option to set up staging server to test, maybe copy the production data there. And the third option, maybe use profilers. So which approach do you use, and maybe in which cases?
Right. Great question. And when somebody tells you that you should measure stuff, you should always ask, how do I measure stuff, right? Or where do I measure stuff? Good question, because you shouldn't probably run your intensive queries if you want to find performance bottlenecks, which means that you're going to run slow queries. You don't want to run it against a live database. Also, you should never run any queries against a live production database, because you can fuck things up. You will at some point, right? We have a replica, and we have a read-only replica, so it's a one-way replication. This replica is plugged into something called Metabase, which is a product that you, like, point to your database, and you can run queries against it. You can also have, like, built-in facilities for some data analytics. So this is something that the, well, data science not exactly, because they get their stuff into Bigtable and use BigQuery, but we have quite a bit of analytics running against this replica database, and we also use it for performance analysis. It has one drawback. Postgres keeps a pretty nice statistics inside. There are like a lot of those like not hidden but like not exposed tables in Postgres, where Postgres actually keeps track of your slowest queries or of your most frequent queries. Postgres even keeps track of how your indexes are used. Have the index been actually, well, A, used at all, and B, how it was used, or how often, or like what sort of savings did you get from your index. The thing is that those metadata, those statistics, those internal Postgres statistics, they are not replicated. They are specific to a running server, and I don't think they're even persisted. I'm not sure about it. Which means that if I want to look at this metadata, I still need to go into the actual live production database, which I'm trying not to, because again, if you have a good enough observability, you can see the slow queries anyway, right? So I'm finding slow queries in our observability stack. Right now it's New Relic. I really don't like New Relic, but this is another conversation. If I find some slow queries, queries that are slow in the P95 or P99 centiles, then I basically replicate them, or like, I basically copy paste them into Metabase. I see if it's happening the same, if it's also slow in Metabase. If not, it might have just been like a caching versus reading from the disk issue. But if they're consistently slow, then of course, like, I do explain analyze, and then I do the entire stack. But I don't use any like dedicated profiler beyond what explain analyze gives me. I hope that answers the question. Again, I'm not a database expert. Scaling a product, it basically means that you kind of have to become half-baked, half-assed expert at a lot of things. Any other questions? Yes.
Thanks again for the talk. I have a bit side question. What's your take on like NoSQL database? Because for such specific like cases like messages, so you only like read and write. You need to like probably delete maybe in some cases, but you like doesn't update them. Maybe it can be useful.
So again, we only have 36 minutes. So like, what sort of the long answer is, well, not the long, the short answer is yes, in case of messages, storing them in NoSQL database might make sense because this table is not very heavily joined. But the sort of like the spicy take is, for every feature of NoSQL databases, I've seen this feature being available in Postgres, while keeping the relational features and similar performance, assuming you still want to write a headlog, so double commit and all the all the features like this. Our messages table, because it basically doesn't join a lot, and it just has like a single foreign key, conversation ID. It's actually super great for partitioning. I can partition it down even to a point of like every conversation having its own partition, right? 20, 100, 200 messages. So I could use a NoSQL database, introducing yet another service, yet another application, another piece of software into our stack, having a different API, having a different way to call it, different way to manage it, different way to operate on this data. Or I could use Postgres just in a bit more advanced way and partition this table. So I don't dislike NoSQL databases. There's a lot of use cases for them. But I think that here we can still go pretty far with Postgres. Like, we're not at the limit of what we can do with Postgres. We can actually still do quite a bit. And also, NoSQL has an extra complex, well, not only NoSQL, but like adding any new solution, like for example, sharding, application level sharding. This adds code to the application, this adds logic to the application. Adding a NoSQL database adds a new adapter, adds a new language, adds a new DSL, adds a new complexity that developers need to be aware of, that developers need to learn. My CTO, and he's very wise actually for it, whenever I tell him that, messages table is like half of our database, over half of our indexes, we should probably do something with it. We should shard our data or something. And his first question is, what solution do you propose that would introduce a minimal or preferably zero knowledge tax on all of the engineering team. And I can actually still do it with Postgres partitioning, with foreign data wrappers. Postgres since version 11 allows you to put partitions of the same table on different machines, different Postgres servers. It's all still routed and acts as a single main server. It's just that foreign data wrapper, whenever there's a query for, let's say with partition for conversation ID, whenever there's a query to this conversation ID, or the conversation ID in the range that's on a given partition, it silently routes the query to this partition, gets the results, serves them back, and my developer, well, our developers don't even need to know that in production actually this table is being partitioned. So NoSQL, yes, in this application, not exactly, not yet. Yes. Let's make it the last question, right? Because I think we are way over time.
You mentioned that Ruby usually is not a problem for scaling, but I a little bit disagree, because it's also possible to write some code which can take your request and response time, like few seconds, minutes, and adding new services it doesn't have. My question is, do you have some performance testing process and how it's implemented, just that engineers not deploy some code which take this, increase this response time for some queries?
Right, great question, and it kind of bites into another topic that I've only alluded to, observability. No, we don't do isolated performance testing, and we don't do it for a reason. The purpose of this talk was to kind of show that performance is a problem when you have a certain amount of data. And doing performance testing properly would require basically running a replica of production on a replica of production database, which is kind of costly, and you would need to build a lot of synthetic tests. The problem with building synthetic tests is that you always test yesterday's problems. You always test problems that you've already solved. And this is a bigger problem of observability. Most of our telemetry tooling that we are used to, like logging, but also like metrics, but also like distributed traces. And this is beautifully covered in Observability Engineering book by Charity Majors, the one with the fox on the cover, which I fully recommend. It's thin. It's very much, to a big part, a pitch of our product, Honeycomb, but it applies to a lot of other observability tooling. But like the approach that she proposes, that she champions, and the approach that I agree with after seeing, because again, we can do performance testing, but against the problems that we have solved already, more or less. Against pages we know are slow, against collections we know could get slow, against tables we know were slow and we have already put indexes on, right? Her approach is, there is a place in engineering stack or workflow or ritual for testing. There's a place for performance testing, there's a place for analysis, for code review. Sure, for staging environments, for QA testing, so like manual or quick testing or automated testing. But the lesson that the observability people, the modern observability, let's say, is trying to pass on and prepare all engineers for is that you can never anticipate problems that your production environment might have, including performance problems. So the idea behind modern observability is build your observability tooling in such a way that it will alert you when there's some performance issue, and that it will show you enough details or enough data to immediately show you what is the cause, or what is the hotspot, what is the cause of the issue, and then fix it. The idea behind modern observability is basically also like empowering engineers. Like you no longer have like release managers or like people with limited privileges. The idea is that the entire team builds it, ships it, and runs it. Which means that everybody writes code. Sure, all of the engineering team writes code. All of the engineering team can deploy and roll back, and all of the engineering team runs it, which means they do observability and they know how to analyze data and observability. So we are not doing performance testing, but this is a conscious decision because we know that performance issues are going to creep up in production, and what we want to do is we want to have an entire technology stack to allow us to quickly be notified about them and quickly investigate them on production data and quickly remove them. So to be reactive, but to be like reactive in a smart and fast way. I hope that was maybe not an agreeable, but at least satisfactory answer to the question. And I think we should finish right now because there's beer to be drunk, right?
Yeah, you still have to use your dots. More dots for the beers. So, thank you, Tomasz.